Welcome to O Morgan Labs, and today we're going to be talking about materials and properties, crystalline structures. So I'm going to get into two basic shapes, the simple cubic and the face-centered cubic. There are more, triclinic, all that other stuff, but these are two of the simplest shapes that you can see. All right, so simple cubic, all of your lengths are the same. Let me put the brush on. All of your lengths are the same here, right? This equals that, equals that, equals that. Everything is equal 90 degrees. It's a cube, right? And and then these are your atoms. Simple cubic. Now, next one is the face-centered cubic. It's almost like the simple cubic, but instead of just having atoms in the corners, you have the same atoms like along the faces, right? You have one, okay, front face, back face, top face, bottom face, left face, right face. Face-centered cubic. And then there's a body-centered cubic where there's one like right in the center. That's going to come up. BCC. That's another way we categorize or name these simple shapes. A crystal is just a repeated shape over and over again. That's the definition of a crystal, when your molecules make a repeated pattern everywhere. So let me write, I guess, simple cubic, face-centered cubic, hexagonal closed packed, body-centered cubic. That's the one with the one in the middle. Now, here's some examples. Cesium chloride. Cesium chloride isn't in a lot, or this type is in a lot of things you would use. See, I should have turned my stuff off. There goes the Uber Eats commercial. Anyway, but it has a simple cubic, right? A lot of compounds have a simple cubic shape. And then you have common table salt. It's a crystal, and it's a face-centered cubic. But the funny thing about this is you have, okay, so the big circles they represent the sodium atoms. Okay? And they make a face-centered cubic pattern shape, right? But you have these chloride atoms. We'll make those green, right? Along these edges, right? But the question is, okay, well, you have all these other things kind of messing up your shape. Why is it still face-centered cubic? Well, if you just stack this basic cube, if you put another cube like right over here, and you concentrated on your Cl atoms, they would make the face-centered cubic shape. Okay? So it would be face-centered cubic. That's the best way I can explain it, because it's kind of confusing, because in my book he says each lattice point, that's like the node if you're thinking about circuits or whatever. But anyway, each little node, or you're thinking about finite element analysis, because this reminds me of finite element analysis. You're dealing with little bricks and stuff in cubes. Anyway, each lattice point represents a pair, an ion pair, and I really didn't get that. But if you think of it in terms of kind of stacking this basic cell, this is kind of like a unit cell, they call it. Unit cell. If you stack these unit cells, you can kind of put like the in-between point, right? I made like that. If you make another one, if you could just say some arbitrary kind of like the in between, this represents like a pair, then you still have your face center cubic, but that's another way of explaining it. I really didn't, it kind of confused me. But the best way I think is just think of it in terms of just this one unit cell, and then just look at the chloride atoms and just think they can swap places, right? Or if you just stack this unit cell with another one and concentrate on the chloride, you'll find you can still get that face center cubic shape. All right, so last thing, coordination number, kind of confusing. Basically, it means if it's 6:6, there's one sodium atom surrounded by 6 chloride. What is it, chlorine or chloride? Chloride atoms around it. It's the shortest distance. So if you look at the unit cell, it's like there's one way out here in Neverland, and you're like, well, why don't they count that one? That's another chloride atom, you know, but it's the shortest distance. So I need to go and do another video, but if we calculate, you can calculate this because crystal structures, they're predictable. You can calculate it. The distances from your sodium atom to your chloride atom, they should all be equal. All these brown lines should be equal, and they should be shorter than well, it's now blue line, the blue line, right? So that's why you don't count the ones kind of, they're near it, but they're not closest to it. Or you think of a circle, just think of a circle, like an invisible circle surrounding the atom, and everything that touches it, that's like its closest neighbor. You think of it that way. Okay. Old Morgan Studios, hope you learned something about material properties and crystalline structures. Like and subscribe.